Okay, sorry about that. I just bumped my microphone off for a second.
I don't usually go through like the autograder graphs, but I wanted to mention one thing for a reason. So on the autograder last night, in the last hour before midnight, we had 175 plus 102. We had 277 submissions in the last hour before midnight. And the reason that's important is don't count on saying, hey, I'll submit at 11:30, I'll get my results back, I'll have like 20 minutes to change my code, and then I'll upload it again. If you upload at 11:30, you might not get the results until after midnight. So just don't count on getting that last submission, 2 submissions in a half hour at the end, because people get, we run 6 jobs at a time, 2 machines, that's 12 jobs at a time, 277 jobs, that's like 20 cycles. And some people spend 5-10 minutes in the queue because they TLE on a bunch of test cases. So just don't count on getting 2 submissions in the last half hour as the project becomes due. So count on like 1 submission from 11 p.m. on. Okay, so on the slides, we didn't quite finish yesterday, so we're gonna do some catching up today, and then we've got a lecture coming up that's gonna be a little bit short, and we'll catch up then. So we looked at the copying last time. So we're talking about, hey, I've got in this array object, I need a copy constructor and an operator equals, and we wrote a straightforward version with having a separate function, but this is not really the best way to do it. So this is the best way to do a copy constructor and an operator equals both. So what we're gonna do is we're gonna write a copy constructor, pretty standard. I use the initializer list. You don't have to, but we can. I use the initializer list for the data and the length, and then I've got a for loop to copy the elements. That's pretty standard. What's different after that is how we are going to do operator equals. So the first thing we did here is we created this swap member function. Now this swap member function does allow for other cool things for me to do. Like I could create 2 arrays. I could say like array X has 10 elements, 10 elements, and array Y has like 20 elements, and then I spend some time filling those in, and I can say like X dot swap Y whoops, y, x.swap y, and it will swap the contents. It'll say, oh, let's swap my data with the other guy's data. Let's swap my length with the other guy's length. And now the contents are swapped because they've changed sizes, they've changed pointers, they've changed all their data. But that's not the motivation. It happens to do that, but here's the real motivation is what we're gonna do next is we're gonna write our operator equals using what's called the copy swap method. So first of all, operator equals says I am going to return an array object reference. Now that hasn't changed from our straightforward method, array ampersand operator equals. And the reason that we return an array reference here, one is that you're allowed to say things like x equals y equals z. And these resolve, they are associative from right to left. So y equals z happens first, that returns a reference to y, and then we can do x equals that reference. So that's why we need to return something rather than void, is so that we can chain equal signs together. And we return an array reference because after y equals z happens, y still exists, there's no reason to copy it, so we return a reference to the object. All right, so there's our statement of the function name. So it's array reference operator equals, I receive a const array reference. So you give me something else, I promise not to change it, I'm just gonna make a copy of it. Then what we do is we say array temp parentheses A. What does line 16 do? Who makes line 16 happen? Yeah. It's the copy constructor. So what we're doing here is we're saying, hey, if you want to make something equal to A, let's start out by making a copy of A by using the copy constructor. So the copy constructor makes a copy of A, then we swap. We say, hey, current object, whoever you are, swap your data with temp's data, and then return a pointer. Now let's draw out what actually happens here. So I say something like array object x has 5 elements, and array object y has 10 elements, and then I do some code to put some values in those. So in memory, what does it look like? X internally has a 5, and it has a pointer to a block of memory with room for 5 values. Y internally has a block of memory that has a 10, and it has a pointer to a block of memory with room for 10 values. So that's what's in memory right now. So then the question is, what happens when later on I say x equals y? So when I say x equals y, okay, let's go back to the previous slide. When I say x equals y, we're invoking operator equals. The first thing we do is create array temp of A. Well, wait a minute, what is A here? When I say x equals y, who is the current object and who is the parameter A? Yeah. For which one? The parameter, yeah. So when I say x equals y, this is a pointer to x, and A, reference A, refers back to y. So anything that we say, when we talk about A, we're talking about the actual object y, and when we say anything about the current object, we're talking about x. So back to our code, it says, make me a temporary object by copying A. Well, A is y, so we create temp. So temp object gets a 10. It gets a pointer to a block of memory of size 10. And let's say this was like 3 and 5 and 7. There were 3, 5, 7. So I would copy the values from the first one. I'd copy them down to temp. So I've created my temp object. So that was the first line of the copy swap method. So create the temporary object A. then swap with temp. So when I call swap, who is the current object? Who is other? Well, the current object hasn't changed. The current object is X. The other object is who? Temp. All right, so we're saying X, swap your stuff with temp's stuff. So what happens is we swap the lengths. So X gets a length of 10, temp gets a length of 5. Then where does X point to? X points to temp's block of memory. Where does temp point to? X's old data. So temp actually now points up here. Okay, so that doesn't exist, that doesn't exist. So X points to this block of memory, temp points back to the original one for X. Then the last thing is return this. When we return from this function, we return this. Well, this is X, so we return a pointer to the current object X. But what happens to temp when we return from this function? Says it in the comments, temp is going to get destroyed. So what happens when temp's destructor gets called? Which block of memory gets destructed? The old block of size 5 gets destroyed. The temp object is now gone. X is left with a copy of those 10 values. So this is what's called the copy swap method, is we make a copy of the thing on the right of the equal sign. So we make a copy of Y, and then we swap X's old data with the copy data. So then when temp gets destroyed, it takes X's old data with it. So there was no reason for me, I didn't have to do a new, I didn't have to do a delete, I didn't have to write a loop, I didn't have to do anything. I just invoke the copy constructor, invoke the swap, and return, and everything's fine. But here's a question. In the old version, we had to have, the idiot check. This version, operator equals, has no idiot check. So the question is now, what happens if someone happens to write code that says X equals X? What happens? We make a copy. We make a copy of X, we throw away the original and inherit the copy. So it used to be everybody paid an idiot check of cost O of 1. Now, in the new method, in the copy swap method, most people pay no cost of an idiot check. But when someone does this, what's the cost of doing an idiotic move like self-assignment? It's O of n. So now bad code costs more and good code costs less to write. That's a win, right? So we've eliminated this constant cost for everybody and imposed a big cost for bad code. And the other nice thing about the copy swap method is it's always the same. If I make a new class and I want to use the copy swap method, I still have to write my copy constructor, but then swap, all I have to do is make sure there's enough lines of swap for every member variable, and then my operator equals, all I have to do is change the name of the object and I'm done. So now I never have to write a new operator equals. My operator equals always just uses a swap and a copy constructor. So now future versions, you don't have to. You don't even have to write swap as a separate function. I could just take these 2 lines of code, put them in here in place of that swap, and get rid of that function. I could make it all one function if I wanted to. So this is the copy swap method of doing copy constructor and operator equals in a very efficient way, and it's very simple to apply to new projects. You just say, oh, I'll look back at lecture 5 slides, I'll search the slides for the word copy-swap, and I'm done. Just do what it says. So when I've got a constructor that involves dynamic memory, so I've written a constructor, my constructor does a new, then I've got to make sure to implement the big three, no, 5. We've got to implement at least the big 3. Big 3 is destructor, copy constructor, operator equals. Got to do those. C++11 provides an optimization for 2 more. You don't have to implement them. If you don't implement them, you just don't get cool speedy stuff. You just do it the old way. So the copy constructors and overloaded operators equals from our values, one nice thing, one important thing to know about them is how they can be used, because you can take advantage of this without ever knowing how to write one. So for instance, suppose I've got a function that's going to return a vector of strings called foo is the name of my function, and it's got some parameters. Well, inside of the implementation for this, I'm probably going to have to create a vector of strings called result. I'm going to have some code that fills in that vector, and then when I'm done, I'll say return result. And then in some other function, I might say something like vector of string, whoops, string, vector of strings x equals foo of whatever. Or I could write this a little bit easier. Instead, I could just say auto, A-U-T, if I could write today, auto x equals foo. And hey, compiler, you figure out that return type for me. Either way, something cool happens. The compiler notices, hey, x doesn't exist yet. So because x doesn't exist yet, and because the result is going to be destroyed, let's not make a copy of that object result. Let's not make a copy of a vector full of string objects that all have to be copied. Instead, what happens is x basically hijacks results data. Result gets a null pointer, and then when result gets destroyed, it destroys nothing, and x has stolen results data. So instead of copying things, when something is about to be destroyed and you're about to make a copy of something about to be destroyed, basically it steals the data instead of copying it. So this is nice. As long as you use like dash standard equals C++11 or 14 or 17 or 1Z, as long as you use standard equals C++11 or beyond on the command line, on the compiler line, you will get this behavior that objects being destroyed don't get copied, their data gets stolen, and that's all because of these R values. So if we write our array class without these things, and we return an array object from a function, we won't get the speed up. Our array object will actually get copied. But if we want to make our array objects even faster, we could go and learn how to implement these. Okay. Oh, shoot, I forgot to fix this. This slide is off very, very slightly. This stuff should all be moved up by 1 line. I goofed on the formatting on this. I changed the code, and I forgot to move the complexity up to match where the code was now. Okay, so we say, if I'm going to construct an array object, well, I've got to create a new double array. That's just a constant amount of time. Creating a block of memory doesn't depend on the length. It's just a fixed amount of time. So we got 1 step to create the new array, another step to copy the length. We've got the loop is going to run n times. So the body of the loop is going to run n times. N is going to be whatever length is. So we've got to loop through and copy everything in the array. And it takes a constant amount of steps to do this line here. Well, that line there involves square brackets, and assignment, so it's like 3 operations basically. So we do the loop runs through n operations, and it doesn't matter. Best case, average case, worst case, we've always got to copy all n elements of the array. We can't skimp and skip over some of the elements. Now, suppose I wanted to make my array class support square brackets. I'd like to be able to write code like this. I want to be able to say things like array sub 0 equals 2.0, I want to be able to treat an array object as if it was an array and supports a square brackets operator. So that's what I do, is I implement operator square brackets. Now the first one here, let's look at the left one, says double reference, operator square brackets, give me an integer index. So if we give it an integer index, it checks the length. If the length is it checks the index. If the index is valid, it returns data subindex, otherwise it throws an exception. And let's look back at the return type. The return type is double reference. So double, because we've got our internal memory is a block of double, we've got a dynamic memory pointer to a block of doubles, but it's reference because in line 2 we want to modify it. So if my array object A, right, inside of A has a 3, which is the size, it's got a pointer to a block of memory of size 3, when I do square brackets, I want to actually return a reference to that element so that I can put 2.0 in there. If I just returned a double, I could look at the contents, but I couldn't change it. And we want to be able to change it, so that's why we return a double reference. Now, if the index is invalid, we throw an exception. Now, the exception is there for one reason, to let people know they had an invalid index and they can go fix their code. But another reason, what would happen if I said, hey, let's take that throw a runtime exception and just replace that with return 0. What happens now? Think about if I pass parameters by reference. If I say, hey, I'm a function, I accept an integer reference, can I call that function with the value 0? Yeah.
0 is like a variable.
It's not a variable. So we're not allowed to return a reference to a constant. We're not allowed to, like if I say I'm a function, I receive an integer by reference. I'm not allowed to call that function with a constant. I'm only allowed to call it with a variable. So the compiler will reject this. If I try to replace this line with return 0, the compiler will reject the function. The important reason why it would reject the function, what would happen if it worked? What would happen if the compiler accepted this change and I executed line 2 at the bottom, and then I was to see out 0 plus 0? What would be the answer? 4. I'd say display 0 plus 0 to display 4. Now, we've learned from our mistakes. Fortran allowed this to happen. So old language, yes, but they made mistakes. They allowed people to change constants to other values. And so we've learned from it, we don't let that happen anymore. So we can't return, whoops, wrong button. We can't return a reference to a constant. We either have to return something that still exists. When this function is over, data sub IDX still exists. It's safe to return a reference to it. Now the other version over here on the right says, I'm not going to return a reference to a double. I'm going to return a const reference to a double, and I'm got another word const over here. So what do these two consts mean in terms of what can be done? Either one of those consts, what do they mean? Yeah. Right, so hold on, one at a time. So the second const says, I am a const member function. I promise I won't change member variables. Okay, then what does the first one mean? I can't, so whoever I return a reference to is not allowed to modify what I give them. So when I give you a const double reference, you can look at the double, but you can't change it. And those both need to be there. If I say, I promise I won't change things, but I give someone double reference that they can change, then I've lied. I'm letting other people use me to change member variables, and that's not allowed. So we need both of those in there. Now the reason we need 2 versions, the code down here, so lines 2 and 3 have to include the modifiable version. I've got to change what's in the array. but in line 4, which versions get used? So when I look at these values here, which version would you think would get used? The const version, right? And when I want to change it, that's got to use the modifiable version. Well, the truth is stranger than fiction. This actually, every compiler I've seen, even this line uses the modifiable version. But next slide. So next slide will show you why we need the const version. So I've got the example up there from a const object for a const double. This is for a const reference. So if we had objects in it, we could change it to const type reference. But the real code is down here. So if I'd say, hey, if you give me an array object, well, I'm not going to output an array object by value. I don't want to copy an array object to output it, so I'm going to pass it by reference. Oh, wait, I don't need to modify an object to output it. I'm going to accept a const reference. So when I want to write an output operator, I say, hey, if you give me an OStream reference and a const array reference to object A, I promise I won't modify object A when I print it. So when I call the .size member function, that must be const. And in fact, if you look back a few slides to the first slide of this class, I declared the size function to be const. And the other one is here, a sub I, the square brackets operator, got to have a const version of that also. So without the const version, this code won't compile. So we've got to have a const version of size. In fact, our only version of size needs to be const. And the square brackets, we've got to have a modifiable version. We got to have a const version so that this code will work. So then we send things to the output stream, and then we return the output stream when we're done by reference. So there's the code for like creating an output operator for our array class. So we can, because we're writing the array class, we can say, hey, if you want to, you can display whatever's in our array class. Because I know it's an array of integers. I know this will work. Now, if I was going to create a 2D class, so I've got my const version up here for my 1D array object. If I was going to create something like, let's say, called array 2D, was my class name, and I wanted to create like an array object A2 that had like 5 rows and 3 columns, and then I want to say something like A2 sub 0, comma 0, well, that's not allowed. The square brackets operator, it turns out, is only allowed to have one parameter. So if we wanted to create a 2D object, we couldn't use square brackets. What we'd have to use instead is we would have to overload operator parentheses. Because operator square brackets is only allowed to have one parameter, but operator parentheses can have as many parameters as you want. So I could say something like A2 parentheses 0, comma 0 equals, say, 2.1. So that would be row 0, column 0. And operator parentheses is allowed to have any number of parameters. Operator square brackets is only allowed to have one parameter. Turns out operator square brackets, the one parameter, can be any type you want. And we'll look at later in the class, we'll look at classes that use different things for operator square brackets. In fact, I'll mention one of them later on. Here's another function. Suppose I wanted to allow someone to insert a value and specify where to insert the value, and I'll move everything over to make room for it. So for instance, I just happen to have created an array object AR, and I just happen to be keeping the values in it in numeric order. So everything I do on this, I'm going to make sure it stays in order. So when I say insert at index to the value 3.4, I want 3.4 to go basically right here. But to do that, I'm going to have to move everything over to make room for it, and I'm going to have to lose the last value because I'm not going to grow my array. It's a fixed size. Our array class is all fixed size so far. So for me to do that, for me to put that 3.4 in there, let's look at the code. It says, check the index. If the index is invalid, return false. Otherwise, do it and return true. We could get rid of that if we wanted to. We could say this function is void, and if the index is invalid, throw an exception. So this one, we could say do nothing. The square brackets, we couldn't do nothing. The square brackets, because we were returning a reference, we either must return a reference to something that still exists, or we have to throw an exception. This one, we could say, oh, I just refuse to do any work if you try to insert something at an invalid index. Okay, so I check if it's in the right range. If not, or sorry, if it is in the right range, we're gonna run through the for loop. So the for loop starts at the back end and basically says, take the 7.3 and overwrite the 8.4 with 7.3. Take the 5.9 and overwrite the 7.3 with 5.9. Take 4.2 and overwrite that 5.9 with 4.2. And that's where we end up right here, is after we've copied every element over by 1. And so the 8.4 has disappeared. Why did we start at the back end and increment to the middle? Why didn't we start in the middle and increment to reach the back end? Why did we go from end to middle instead of middle to end? Yeah. Yeah, I'd be losing values. I'd say 4.2 overwrites 5.9, which loses 5.9, so I've got to make a temp variable. I've got to remember 5.9, then overwrite it, then I've got to remember 7.3 and overwrite that. I have to a bunch of temp variables and more complicated code. So it's just a lot simpler to go from the right end and overwrite each value one at a time than have temporary variables. So it just became a lot simpler. So I copy everything over by 1 position, the 8.4 gets overwritten and I don't have it anymore. And then after we're done, we take this original 4.2 and overwrite it with the 3.4 we wanted to insert. And if we're going to do lots of insertions, is array the best data structure to use for this? If I'm going to do insertions in the middle, what would you expect would be better? Like something like a linked list? It turns out that's about the only time you might use a linked list. We're going to look at, we got another set of slides coming up that'll have a bunch of timing information about using different data structures and using different operations on those data structures. It turns out linked list is almost never the answer. It's inefficient in a lot of cases. Not everything, but most things. So when we did this inserting an element, what's our complexity? Well, the best case would be if I say, hey, insert a value at index length -1. So in this one, for example, the length is 6. In this example, if I said insert at index 5, then the for loop doesn't have to run and we get insert as O of 1. Worst case would be index 0, insert at the beginning. I've got to move everything over. Average case would be where? About the middle, yeah. So the average case is going to be n over 2, but still O of n. The worst case is O of n, best is O of 1. Remember, when we do best, worst, average, we're not allowed to change n. We're only allowed to change the other things, like where they're going to insert. So the size is unknown at n, but we can change where they do the insert to get a different best case or worst case. Now, what if I said, hey, I would like to append a value to my array object? Well, if there's no room for it, then either we're out of luck or we've got to add some more complicated operations. We could replace the word append here. We could say instead of append, we could say push back. Yeah, this would be like a vector, push back on a vector. So if we say let's push back on a vector and there's no room for this new element, well, then what we've got to do is we've got to create a new array that's bigger than the old one. Then after we've got that new array created, we can copy all of the elements over from the old one. Then we can copy the new element and put it in where it belongs. And then after the copy is done, then we've got to delete that old block of memory. We don't want a memory leak. So we delete the old block of memory and then we change. Remember, we used to have a data member variable. My data member variable used to point up there. Well, it doesn't point there anymore. Now my data member variable points to this new block of memory. So why did we have to make a new array? Well, that's simple. There just wasn't room for a new element. The question is, though, why did we make it twice as big? Why not just say, hey, you want to add one element, I'll just make it bigger by 1. We'll go from 5 to 6. We'll go from 6 to 7, 7 to 8, 8 to 9, 9 to 10. Why didn't we do it that way? Why did we double the size? Yeah.
Because you
You have to copy every time, and we're making a bet. We're betting that if it's full and you want to add one element, you'll probably want to add a couple more in the future. So if we were to grow by 1 every time, what would be the complexity of pushback? It'd be O of n, right? And that would be a big pushback. So instead, we double it, and we're going to analyze the complexity in just a minute if we double it. Why did we double it instead of, say, multiplying by 10? Why multiply by 2 instead of 10? Yeah, we might, what? It'd be too much. We might waste too much memory. So we're trying to find a balance here. We don't want pushback to be O of n, which would be what happened if we would just grow by 1, but we don't want to have too much wasted memory. So if I go from like 1,000 to 2,000 and only use 10 elements, and I'm like 45% wasted memory, I'm kind of okay with that. But if I went from 1,000 to 10,000 and only added 10 elements, then I would be basically 90% wasted, and that I would be unhappy with. So we're trying to strike a balance here between we don't want pushback to take too long, but we don't want pushback to waste too much memory. And the twice is very, very common. I've seen one implementation of the STL that did multiply by 1.5, and then that compiler's very next version doubled instead of 1.5. So it's very, very standard to double the size now. So let's look at what happens. So let's suppose that I'm at size n. And by n, let's change that slightly. I'm at size n out of n. I've got n elements in use out of a size of n. So if I do that, to grow that vector, what I need to do is I need to double the size. So now I need to become basically n out of 2n, and then I can immediately proceed to n plus 1 out of 2n. So I'll go from n out of n to n plus 1 out of 2n to n plus 2 out of 2n, etc. Now, after I grow it, so if we think of this as 2 different steps, if you're full, you grow, then you push back whatever you want. Think of it as 2 steps. I grow it, so I copy it to a bigger size, and then after it's grown, I can append n new elements. Remember, I went from n out of n to n out of 2n. Now I can finish n pushback operations before I'm full again. So let's look at what that process looks like. If we look at the size on the x-axis here, whoops, I'm going to need to, a little bit off, I need to label things below that. So this is size on the x-axis, this is time on the y-axis. So if I'm at n out of n, and I need to grow that vector, well, I need, whoops, too long a line there. I need basically n time. It takes me n time to grow that array, but then I can go up to n plus 1 out of 2n. How long does it take to go to n plus 1 out of 2n? How many operations? Just 1. I just have to add that value and increment this integer. So it's basically 2 operations, so it's basically O of 1. So there's 1 operation to do there. How much to go to n plus 2 out of 2n? 1 operation. All the way up to, until I get to 2n out of 2n, everything up here just costs 1 until I get to 2n out of 2n. Once I get to full again, how long does it take to grow the array? 2n, yeah. So now it costs twice as much to grow it. This is 2n. But think about it in terms of one sort of life cycle. From right here, from right before I had to grow it until right before I had to grow it again, what happened in here? How much work, how much total work is in that box? It's n plus 1 plus 1 plus 1. How many of those ones are there? There's n of them equals 2n. So my total amount of work was 2n. How many pushbacks? How many pushbacks was I able to do? N, right? I was able to go from n out of n to n plus 1 out of 2n to n plus 2 out of 2n. I was able to finish n more pushbacks. So what's the, not average, amortized cost of pushback? Would be 2n divided by n is equal to 2, says O of 1. So even if you start out with an empty vector and push and push and push and push, each push has an amortized cost of O of 1. It takes 2 operations. So what if instead, what if I were to reserve the right size up front and do exactly that many pushbacks? It would still be O of n. But if I reserve it, that's 1 operation, then every push is 1 operation. But if I don't reserve it, every push is 2 operations. So the pushing takes a little bit longer, basically almost twice as long to go from 0 out of 0 to n out of n as to go from 0 out of n to n out of n. So the reserve does make it a bit faster, not a huge amount. When we're talking like a program that reads some data and then does a bunch of processing, the reading is kind of small anyway. So whether the reading is like 0.01 seconds or 0.02 seconds, not that big of a deal. The reserve is nice, but in terms of speed, it's not huge. Where does the reserve really win for us then? In memory, right? What if I say I want a reserve of like 1025? Well, then I get exactly the right size. But if I don't do the reserve, I go from 0 to 1 to 2 to 4 to 8, up to 1024, up to 1025 out of 2048. I'm basically 50% wasted space. So reserving does better for us, more important stuff for us in terms of memory than in terms of time. Assuming that the other stuff that happens after the reading is going to take longer than the reading, whether we reserve or not a big deal in time, but it could be a big deal in memory. So like when you've got in project 1, if you've got like a simple dictionary that says 1025, you want to reserve 1025. What about a complex dictionary of 1025? Well, just use what it says. We don't have a better guess for our solution than you have for yours. So I just said, oh, use whatever I read, that's the size I want. And if I'm wrong, if it has to grow, we both grow the same way. The vector, when the vector's full, the vector grows when I push back another word. So it's not a big deal there on time, but the memory could be important on the savings there. Okay, so there's a few questions here you can look at about things, about the slides, and then we're going to go to the STL slides and talk more about the STL. Okay, so the standard template library is, good question, is why do we use it? So there's a quote here basically talking about how programming has gotten easier because of the STL. So the C++ STL was the first major language to make a standard library part of the package. Now at the very, very beginning, you had to download like GCC and the STL separately, and then a few versions later, they were just always packaged together. But basically, it was the first language to include this standard template library. And then other languages that came afterward copied that scheme. When Java was designed, Java copied a lot of the things that were in the STL. They made Java versions of them. Then they added more stuff, like for graphical user interfaces, et cetera. And when Microsoft developed C#, they developed C# off of basically Java. And it was, again, inheriting a lot of the ideas from the STL plus user interface stuff. So the libraries that we get, for certain things, it's really important to use the STL. In previous years, so I've been teaching 281 for 5 years now. Before I got to U of M, different professors would teach 281 different semesters, and they all had different ideas. So one semester, the professor would say, okay, it's project 1 time, you've got to write a linked list so that you can have a deck, and you've got to write a growable object so that you can have a vector, and then you can do the project 1 stuff. And the next semester, the professor would come in and say, hey, let's just use the vector and the deck and everything else. The problem was then you get to an upper level class, and the professor in the upper level class says, so you all know how to use vector, right? And half of the students say no, and half of them say yes. And so the upper level classes hated that. They love now that 281 is very consistent from semester to semester, and what we cover makes it a lot easier for the upper level classes to know what you know, or at least what you should know. Is pretty consistent. So STL stands for Standard Template Library. It's been included with C++ basically since the beginning. C++ 11 made a big change to what was in the library. C++ 11 added a lot to the library. Every version of C++ expands the language a little bit. Every version of the STL, or sorry, every version of C++, the STL improves incrementally, but C++ not only improved incrementally, but added a bunch of things that weren't there before. It's very well documented. It's got very, very good implementations of data structures and algorithms that you can go and use. And so we want to do a lot of learning in this class on how to use the STL is beneficial to us. On project 2, you're going to use the STL, parts of the STL, and we're going to have you implement some of your own classes that are basically going to be templated. We're going to give you the headers up front. You just have to fill in the member function code for it. Now, because the standard template library is written as templates, for templates to compile, all source code must be visible at compile time. So there's no linking necessary for the STL as there are with things like the POW function needs the CMath library to be linked to it. The other thing about this is the STL, all the code is out there. If you've got Visual Studio or Xcode, you can say, create a vector, vector.pushback, and start the debugger and step into pushback, and you can go see the code. It's a bit ugly at first. It's hard to get used to how they write code and how to read it. It's a little bit more complicated than code we would write because it's been optimized over and over and over again. And so things that you wouldn't think of, they have. So the code is a little bit hard to read, but it's all there if you want to look at it. And I've dug through a lot of the STL, except I have one nemesis in the STL, but most of the other stuff that I've looked at, I understand now. So what does the STL have in it? Containers. So containers we've already started using, right? We've got vector, deck in project 1, and we might have like linked lists, etc. Iterators are, we're going to talk more about iterators today. Iterators are sort of a generalization of pointers that we can use to walk over some container's contents. So a vector iterator will let you walk over a vector's contents. Decks have iterators, linked lists have iterators. Stacks and queues don't have iterators. You're not allowed to look at every element of a stack. You're only allowed to look at the top of the stack or the front of the queue. Memory allocators. You're actually allowed to do things like say, hey, I'd like to create a vector of ints, and I'd like that vector to use my version of new instead of the standard version of new. Don't do that. Utilities and function objects. So utilities are small tools, like for instance, swap. If you'd like to change the values of 2 integers, you don't have to say int temp equals a equals b equals temp. You just say swap parentheses a comma b, and there's a utility for that. There's a utility for max. You give max 2 variables of the same type, it returns the bigger one. Function objects. So function objects you've looked at in 280 of creating a structure that overloads what? Function objects or functors overload operator parentheses. So we're going to use these things. We're going to use function objects to help us when the STL doesn't have enough to do what we want to do. Algorithms. So algorithms are bigger than utilities. Utilities are like one line of code. Algorithms are things like sort. I'd like you to sort my data, or I'd like you to find the maximum element in this container. The references, so C++ language, 4th or 5th edition, so there's, and he owes us another one after that because the 4th edition is C++ 11, 5th edition would be C++ 14, and I think he still owes us a C++ 17 edition. So the C++ programming language by Bjarne Stroustrup. Stroustrup is the guy who designed the language. And it turns out that all good languages that have really stood the test of time have been designed by 1 or 2 people. So C was designed by 2 people, C++, 1 person, Java, primarily 1 person. Languages that looked like good ideas but have died out over time, like Ada. The Ada language was designed by committee, and it shows. It's got every possible thing in it. Even things that no one would ever use, it's in there because it was designed by committee. And things designed by 1 person tend to be a lot leaner and more efficient. So we got the Bjarne Stroustrup, we got the Joe Sudas, which we suggest as a reference for this class. You can also look at CPP reference or cplus.com. They pretty much contain equivalent info. I find CPP reference to be a little bit faster in my browser, although they've been speeding up C++ lately. It seems to be pretty good now. But they both basically have the same information, same types of examples, etc. The reasons why we would want to use the STL is, well, some of those things in it, some of those algorithms and data structures are just hard to implement. So intro sort is one of the common ways that the STL sort, so the standard sort, is often implemented by intro sort. We're going to talk about intro sort a little bit later on after we talk about a few other sorting methods. Red-black trees are what's called a self-balancing binary tree. So if you insert like 1,000 elements into a red-black tree, you will never just get a big stick that goes right, 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 right. At some point, it will rebalance along the way, and it'll become a tree again. And then you make it a little more stick-like, it'll rebalance back into a tree again. So those are actually really hard to implement. Some things are hard to implement really well. So hash tables are one of the things that was added in C++ 11 that didn't exist before. It's really, really hard to make a good hash table that works well for everyone. So the STL people resisted for years. They said, no, we're not going to add hash tables to the STL. It's hard to write a good one for everyone, just write your own. And people kept complaining for years and years. Finally, the STL group gave in and wrote an STL implementation of hash tables. And they set out with certain goals, and they wrote a data structure that met those goals. Now, is it the fastest hash table? No. Google has what they call the Google template library, has like 3 different versions of of hash tables for different purposes. One's implemented for speed, and it has less features than the STL hash table, but it's faster. Merge sort, which is what the STL commonly uses for stable sort. We're going to look at merge sort. Merge sort is really easy to write. It's like 4 or 5 lines of code. And merge itself can be done in like 10, 12 lines of code if you don't mind using extra memory. But if you want to do an in-place merge, very, very, very hard. Another nice thing about the STL is that it has a lot of uniformity, like max and swap, except 2 parameters. Find me the maximum of these 2 variables, swap these 2 variables, etc. There's things like set union, set intersection, set difference, symmetric difference, etc., all exactly the same types of parameters to do all those different set operations. There's things like min element and max element. You give it a container, it gives you back the minimum and maximum element in that container. And so using the STL can really reduce your time for a complicated program. If we had to go implement a bunch of things like linked lists and vectors, et cetera, before we could write project one, we'd be spending a lot of time on those data structures. Instead, we want to spend a lot of time learning what's in the STL and how to use it. And so these high quality libraries are very well debugged, very well tested, and after X 20 some years of revisions to them, they're pretty much free of bugs. If you think you've found a bug in the STL, the bug is almost guaranteed to be in your code. You made a mistake before you got to the STL. Now, the downside to these general purpose libraries is that they are general purpose implementations. So sometimes if we know something about our own data, we might be able to write a more efficient version. So for instance, if I told you, hey, we need to write a sort for a phone, and the way it's going to be used is your contact list is always going to be, instead of alphabetical order, your contact list is always going to have the person you call the most is at the top of the list so that you can get to them quickly. Well, if we said, hey, I've got friends that I've called 10 times, 10 times, 10 times, 10 times, 10 times, and I call this one more time, I don't need a general purpose sort for this. Oh, and I've got like a 9 down here. Say I've got a 5 down there. If I call this person an 11th time, I have to sort basically after every phone call, but there can only be one person out of order, right? The one person I called. The 5 might have become a 6, no one's out of order, or one of the 10s could have become an 11, one of those is out of order. I don't need a big general purpose STL sort that's n log n. I can do this in what time? I could do it in O of n time. Basically, one pass of bubble sort and I'm done. Just go from this point up to the top, bubble, bubble, bubble. Oh, look, the 11's up at the top. I'm done with one pass of bubble sort. So sometimes knowing something about the data, you can write a much more efficient algorithm than the general purpose that works for everything. So the trade-offs of using this library is we need to understand the library. We need to know what's there. What are the data structures that are there? What are the algorithms that are there? What is the complexity of those operations that those data structures and algorithms do? Both of those sites, CPP reference, C++, have, you look at like, I want to look at vector pushback, it'll tell you vector pushback, complexity, amortized O of 1. And so it's really, really easy to look up complexities of things there. You just have to take the time. STL sort. Now, sometimes it's good to know the details of these. So STL sort is required. It must be O of n log n. How it's implemented after that is up to the person implementing it. So we're going to look at an implementation, how to implement the STL sort called intro sort. We'll look at that in another couple lectures. And in general, the STL sort is going to be faster than quicksort. And even if it uses quicksort, we're going to make sure it's faster than quicksort. The STL nth element is really, really a clever function. Basically, what nth element does is you give it, you say, hey, I've got this list of 1,000,000 elements, and I want that one in the right place. I want element 990,902 to be in the right place. And it does it in average case linear time. It'll get that element in the right place. And it's a bit tricky how it does it in that time, in O of n time, is pretty cool, but hard to implement. But it's important to know that complexity if you need to know nth element. Other things like STL, older versions, linked lists didn't store their size. New versions do. We'll have a summary of those in a minute. So how do you learn the STL? Well, look at a site, pick one, CPP reference, C++. Start looking at some of the examples in there. And if you look at it, so you say, hey, I want to look up vector reserve, there's an example, like 5, 6 lines of code of using vector reserve. Take that, copy it, paste it into your test project in Xcode, Visual Studio, and try it out, add to it, try different things that you can do with it. So try it with different data structures, like can I do this, can I do a reserve on a linked list? Or can I only do resize on a linked list? What about a deck? Turns out you cannot reserve a deck. You can resize a deck, but you can't reserve it. So there's different things that you can do with some data structures than others. And the books like Strew, Strip, Josutis have really good stuff in them, but also you can just go to the websites like C++, CPP reference. So unless you're one of those few individuals that has an eidetic memory, you're not gonna memorize all of the STL. What we wanna do is start learning it by looking at what's there. Just figure out which website you like and learn how to use it. Study what seems interesting. Well, let's see, interesting at the beginning is probably, I need it for the project, but then you'll branch out from there. So you learn how to use the pieces that you want, and in the meantime, you're also learning more about other things that are similar to what you have. So vector has a resize function, dec has a resize. Vector has O of 1 square brackets, dec has O of 1 square brackets operator. Vector has pushback, dec has pushback and push front. So lots of the things that are in there are similar in different containers. So what's useful is learning how to find the information you need when you need it. So some of the language features. So in the STL, writing the STL depended upon certain features of the C++ language. So one of them is bool. Lots of things are important for bool. Like if you want to say, I've got a employee object and sort doesn't know how to sort employee objects, so I will provide a functor. What does your functor return? Bool. So the sort says, here's two objects. Should A come before B, you say true or false. Const correctness. So we already hit on that when we did the array example, right? We said size had to be a const member function, operator square brackets. We need a const version of operator square brackets for certain things to work. So in fact, when we write functors, I'm gonna show you when we write a functor where you have to include the word const for it to always work. If you leave off some of those word consts, sometimes it'll compile, sometimes it won't. Namespaces. So in the STL, most things are in namespace standard. There are a few other namespaces with limited use, but most things are in namespace standard. You can, if you want to, say using namespace standard, and what that means is says, take everything that's in standard that I've included and pull it into my namespace. It can be slightly dangerous at times. So let's say I'm gonna write a function that's like double distance, and I'm gonna give it like const point reference A, and another one, const point reference B. And I write it, and I compute a Euclidean distance between like, a dot x and a dot y, and I do the whole Euclidean distance, I return the double, and I compile it, and the compiler gives me this weird message that it was trying to determine which version of distance to use and whether it should use this distance that accepts 2 points or this distance function that accepts 2 iterators. Turns out the STL already has a function called distance that accepts 2 iterators of the same type, which means it'll accept 2 anything of the same type, and you can't compile because yours has the same name as standard distance. So using namespace standard, I tend to do it all the time, and then if I do something like this, I deal with it on a case-by-case basis. But it is sometimes, it clutters the namespace if you do using namespace standard. Yeah?
Wouldn't the compiler see that this has a different signature than
Nope, because the parameter types are the same. This one accepts 2 objects of the same type. The templated version accepts 2 parameters of the same type. And so it doesn't know, when you say call distance with 2 things of the same type, it doesn't know whether you use this one or the STL one. It's ambiguous. So using namespace standard sometimes produces compiler problems for you. Not very often, but every once in a while it does. Templates, well, the entire STL is written in templates. Everything in the STL is templated to accept different types. Vector of int, vector of strings, vector of employee objects, whatever you want to do. The inline functions, because templates must be visible at compile time. All the source code is there. When you say -03 to your compiler, it does inlining of everything possible, which means your executable gets larger. If your program calls sort twice, sort gets inlined twice into your program, which means your executable gets larger, but it runs faster. Exception handling, the C++ STL doesn't do a lot of it built in. Exception handling, it doesn't use exceptions a lot internally. I think Java did a better job of that. So we've showed you a little bit how to use exceptions in your code, but the STL doesn't use them a lot. The Visual Studio actually uses them more than the standard. The Visual Studio template library, if you say vector sub I and I is out of range, it throws an exception and halts the debugger and lets you debug immediately instead of having to use valgrind. And then if you say, I want a release build, all that goes away. Implicit initialization. We'll look at a little later how to do this, but the idea of it is, let's say I create a vector of int v, and then I say v.resize to 3. What happens internally is v basically says, my size is 3 out of 3, and I've got a pointer to a block of memory, and when you do this, when you resize it, it implicitly initializes every one of those elements to 0. So when you say resize, that happens. If it was string objects, they would all get constructed to be empty strings. If they're integers, they all get initialized to 0. Doubles would be 0.0. What if I had a vector of Booleans? What would you expect their default values to be? Probably false, right? If everything gets zeroed, a vector of Booleans would get all falses. So I'll show you a little bit later how to do implicit initialization in your own class. Operator overloading, so some things use that, like vectors and decks use overloaded operator square brackets to do the indexing operation. And there's other things that do operator overloading, like string objects have plus and plus equals to do concatenation. There's extra syntax for new, like I mentioned, you can write your own versions of new and delete and use yours instead of the library versions. Probably not something you will ever need to do. Explicit and mutable, I made an extra slide for those. So explicit, this is one example. This is not the only example of where it's used, but this is one really good example of use of explicit. So if I have a constructor, so I write my own class, my class has a constructor, and that constructor accepts one parameter. Well then, it's either a copy constructor because the type is the same type as the class, or it's a different type. If it's a different type and it's one parameter, it's what's called a convert constructor. So here, if I've got a feet inches, let's say I've got a class called feet inches that maintains, like 3 feet 6 inches. If I try to initialize it from one measurement, this is a convert constructor. It's converting from a single integer into a feet inches object. And if I declare my constructor explicit, then this is allowed. I'm allowed to say, create me an object and call the constructor that accepts an integer, but this is not allowed because I'm trying to convert from an integer to a feet inches. Another example of where explicit would prevent it. If I had a function, like I've got a function foo that expects to be given a feet inches object, and I call foo of 3, the compiler will say, no, you can't call foo of 3. That would break the requirement that you explicitly convert things. So this is important because you don't want things to be converted without knowing it. Why would that be dangerous? Oh, I don't know, maybe the Mars orbiter crash. Anyone know what happened there? Why we spent millions of dollars to send a probe to Mars and crash it into the surface? 2 different groups wrote the code. Yeah.
One was in meters and one was in yards.
Yeah. No, actually, I think it was in feet. It was actually speeds, but for a simple example, like if I assume I'm 100 meters above the surface, I'm still safe. I don't have to turn on the engine to slow down yet. But in actuality, the people measuring the distance measure it in feet. Oh, I'm actually 100 feet from the surface, not 100 meters, bam. So if instead they had created objects and I said, oh, I'm expecting to receive a meters object and someone calls me with a feet inches object and there's no conversion being done, no, it can't be converted implicitly. You can't call that function with a feet inches measurement. Instead, they just did everything as what? Doubles. Yeah, everything was doubles and there's no, and everything was just in doubles. So in fact, Google's coding guidelines say, all one parameter convert constructors must be declared explicit. Every single thing written at Google, if it's a convert constructor, it's got to be an explicit one. Yeah.
So this is what, like what always yells at me for saying explicit conversion from size to
Or it's saying, no, that's actually because we specified the W conversion flag in the make file. But the reason we did that is in previous semesters, we've had students that ran into just almost undebuggable problems because they did these implicit conversions instead of doing them explicitly. And so that's why we added the W conversion flag. But even without the W conversion flag, this is still an error. So like I said, like Google requires you to write code using explicit for all convert constructors because it's dangerous to do otherwise and it leads to code that's just terrible to debug. The mutable, so mutable is something else, and we're going to give you, when we give you the starter code for project 2, there will be an unsorted priority queue that's already written that uses mutable and you can look at what it does. But basically, when you say, I have a mutable member variable, like I've got class X, and inside of class X, I say mutable int X, this integer X is allowed to be modified by any member function, even if it's const. So for instance, if I tell you this member function must be const, you're not allowed to change that. I've already written the interface, you must follow my interface. Your implementation must be const. But then in writing it, you realize, wow, if I could modify this, if I could create my own member variable X and modify it, I could make the code twice as fast. And I say, no, you can't change the const. You say, fine, I'll make my X mutable, then my const member function can change X. So this gets around constness, and it's only allowed for member variables. So a class's member variable can be made mutable, which means any const member function of that class can modify it. Even if you pass it, like you pass a class X object by const reference to another function, that function can call a const member function that goes and modifies X. But only, it can only modify the mutable objects. When we look at programming in using the STL, one of the things that we're going to do is the STL lets us get away from pointers. There might still be some cases where we have to use pointers, but the STL itself hides a lot of that from us. So when we create a vector, we don't have to really know that behind the scenes the vector has a current size, a maximum size, and a pointer, and that if the size is full, the pointer allocates a new block and blah, blah, blah. All that happens for us. We can ignore debugging the growth of a vector. It's already been done. The other nice thing is that we can reuse algorithms with multiple data structures. So I'm going to show you in a little bit like how to sort an array and how to sort a vector. It's almost the same. This reusing the same algorithms with different data structures, it can be very difficult in C. That's one of the things that like 381 spends a bunch of time on is how do we do this generic type programming without C++ and just pure C. And it can be done, but it's hard to do. So one of the ways that we cut down on knowing on the details also is by using iterators. And iterators are just a generalization of pointers, which we'll look at in a few minutes. The STL implementations of the algorithms and data structures are really, really not just they have the best big O complexity they can, but they are really hard to beat the speed. The STL performance is very, very hard to beat. So in project 2, one of the things we're going to have you implement is a binary heap priority queue. And so I wrote the solution for it. I wrote my binary PQ. And I wrote a pretty straightforward solution, use that for timing. That's what you guys are based on. But then I went, hey, I wonder if I can speed it up. And I said, well, actually, do I need to speed it up? Let's compare my implementation to the STL. And the STL was like 15% faster than mine. I said, I can do better than that. I'm not going to time the students against it, but I just want to write the best version I can just for my own testing, you know? So I got it, I improved it, I improved it, I improved it. I'm like 5% slower and I see nothing left to change. So I went and dug into the STL. I said, okay, that's it. I've done as much as I can think of. Let's dig into the STL code. Oh, yeah, I did that too. I saw that. I'm doing all the same things they are, and theirs is still faster. Why? Because they did iterators and I didn't. I actually used square brackets. If I had done iterators, I can probably reach the STL speed. But it's really, really hard to beat the STL speed, even when you know what you're doing, because it wasn't written by one person. It's been optimized over 20 years by 100 different people. So using the STL really is hard to beat the speed on it. So what are some of the containers in the STL? Well, vector and deck. We're already using those for project 1. If you say, well, I don't want to learn about that deck stuff. I'm just going to create a stack or a queue. When you say create me a stack or a queue, what do you actually get? You get a deck. You get a deck that you're only allowed to push and pop at certain positions, but really what's behind the scenes is a deck. It's just an adapter. So stack and queue are adapters that use deck as their default for their underlying container. Another container type, there's something called bit vector and vector of bool. Bit vector is just a specialization, another name for saying vector of bool. It turns out when you say to the STL, create me a vector of bool, it doesn't use 1 byte per Boolean, it uses 1 bit per Boolean and compresses them. If we use sets, so sets are actually based around balanced binary trees. So set is basically the math concept. A set doesn't have duplicate elements. A multiset is allowed to have duplicate elements. And there's also, so a set and a multiset is a balanced binary tree. Unordered versions of these, unordered set, unordered multiset, use hash tables. Map, so map and multimap also use balanced binary trees. What a map is it allows you to create a mapping of 2 data types from one to the other. So if I create a map of string comma int, I can say like months square bracket the string January and it returns the value 31. So every string that I square bracket is associated with an integer value that I can look up. And if I did a multi-map, then February could be associated with 28. February is also associated with 29. So multi-map allows duplicate keys which map to different values. The unordered versions of these are hash tables, run faster. Linked lists, so the STL has a linked list. It actually has 3 different versions of list. Array, we mentioned before, arrays aren't very useful because they're a totally fixed size, which isn't useful most of the time. So the STL has 3 different versions of list. There's list, slist, and forward list. So list is the sort of standard, doubly linked list, O of 1. If you call size, it's O of 1. Slist is a singly linked list. The size can be O of n, but it's almost always O of 1. Forward list is another singly linked list that doesn't even have a size. It's just for keeping a list of things. Don't ever use slist because slist includes smart pointers. On the autograder, if you see something like, test case blah, and your time and your memory are fine, and you get like 0.1 out of 1.0, there'll be a message below it that says, look at the compiler warnings. So if you use smart pointers, the autograder deducts 90% of your score off the top of everything. So it'll provide a warning. Like every test case will say, look back at the make output, and the make output will say, you're using a prohibited library. So what are some of the things in the STL that we can use simply? So I included vector, and I included algorithm. Algorithm gets me sort and copy and other stuff. And I said, hey, let's create a vector of a certain size. Let's create an array of the same size. Let's fill the vector with values. This is sort of a cheapo way, like j cubed modulo n. It's sort of a cheapo way to put some random-ish numbers in there. And then I want to copy. So I say, hey, I'd like to copy from V, the vector, over to the array AR. That's what this line is doing. So copy expects to be given 2 parameters. It expects, so when we say copy, it expects to be given 3 things. We need the from start, the from end, and the destination start. So when we say copy, that's the 3 things we need to give it. And one thing that's really important to know about these is that the start and the end of the from is inclusive on the left, exclusive on the right. The STL uses that basically for almost anything. When you say do something to this container, you always have to say inclusive beginning, exclusive ending, and the STL member functions begin and end do that. Begin is an iterator to the beginning, and end is an iterator to just past the end. And then for the destination, so I say copy from V begin to V end is where I'm going to copy from. The destination is going to be AR. That's the start of the destination. AR, remember, is a pointer to the beginning of the array. No size checks. If vector is size 1,000 and AR is size 100, that's your fault. That's not copy's fault. Now, the copy back, line 13 here, is not needed. I just wanted to show you if I had put it in the array and wanted to copy from the array over to the vector, this is how you would do it. So the destination start, or sorry, the from, the source beginning would be AR, the pointer to the beginning. AR plus N is just past the end of the array. And then where do I store the result? The destination is going to be v.begin is where it should go. And for this to work, the vector must be the correct size. The array that I'm copying from, AR to AR plus N, the vector must be the same size or bigger. It would be fine if the destination's bigger, it just can't be smaller. Then what about sort? I call sort, I give it again. A begin inclusive and end exclusive of the region to sort, either the array or the vector. And the last one here, this is one way, just one way to reverse a vector. So what I'm doing here is I'm saying the vector object has a constructor that expects to be given 2 iterators. So I'm giving it 2 iterators. It turns out R begin is a reverse beginning of the vector. R end is a reverse ending iterator. So I could say copy this vector to the other vector, but go backwards. We could do it a different way. We could say like reversed equals V, and then we could call STL reverse of V dot, or sorry, reverse dot begin and reverse dot end. In fact, you could do this in project 1. This could be like word dot begin and word dot end. For the ampersand, get rid of the ampersand with pop back, call STL reverse will produce the reverse word for you. And it does it in place. It takes the word that you've got, reverses it from beginning to end. Okay, we're out of time here. We'll pick up on types of iterators next time. Did you do reserve or resize?
Reserve.
That shouldn't happen. But what I would do is like use your
Yeah, like I would use the Xcode debugger to check and look at the vector, or if you're not using Xcode, you could put in some debug and print statements. But look at how you're getting, so are you getting like as many blank lines as you are real lines?
I don't do except because like the dictionary is 4,300 words, and I'm getting 4,800, and the first 500 from artists.